Spectrophotometry. My guess is most of you have used a spectrophotometer already. They are used in most chemistry courses. They are used in most microbiology courses. So my guess is most of you are pretty familiar with this. We're not going to do a wet lab today. I'm only just going to briefly go over the theory behind the spectrophotometer. And next class meeting on Wednesday, I'm going to give you an exercise to do where you're going to be doing some graphs. All that will be included on the first lab test. But let's cover the theory behind it. The spectrophotometer the spectrophotometer is also known as a colorimeter, and it is the classic device used to measure the concentration of chemicals in a solution. Here's really our broader question. This is our broader question. We've been learning what the normal sugar level is in the blood. Anybody remember what the normal sugar level in the blood is? 100 milligrams of glucose per deciliter of blood, or per 100 milliliters of blood. And you should know that. We've been learning what the normal potassium ion concentration in blood and other extracellular fluids is. What's the normal potassium level? About 5 milliequivalents per liter. We've been learning what the normal cholesterol level is. It should be below 200 milligrams %. So we've been learning a number of normal values, and obviously when you run blood tests, they measure the cholesterol level and the glucose level and the sodium and the potassium levels in your blood to see if they fall within normal range. The question is, how do they figure that out? How do they determine what the sugar level, what the potassium level, what the cholesterol level is in your bloodstream? And the answer is they use a device called a spectrophotometer. If we look on page 2, the most common device that's used at the college level looks like this. The only difference between this picture and the devices most commonly used today is that this is an older analog model, and the newer models use digital readout. Other than that, it's absolutely identical. I want to draw your attention to an interesting knob. There is a wavelength control on the spectrophotometer. Why is there a wavelength control? I'll get to in just a little bit. What is the theory behind this device? How is it used to determine what the sugar, what the potassium level, what the cholesterol level is in the bloodstream? So let's look at this picture right here. Basically, all that the device consists of is a photoelectric cell connected to a galvanometer. And you're thinking, what's a photoelectric cell? Something that is sensitive to light. What is a galvanometer? It's simply a gauge. A gauge. Together, all that they really are is a light meter. Now, most of us are kind of familiar with the idea of light meters. They use them in photography. Built into most modern cameras is a light meter. So that, but in a classic light meter that would be used by a photographer, if they point the light meter towards a light, the little needle moves, indicating it's bright. And if they turn the light meter down towards the shade, the little needle on the light meter indicates that there's less light. That's really all that this photoelectric cell and that gauge is a light meter. Now, here's the theory behind the device. We have a light bulb. That wasn't drawn on the picture, but I just drew it in here. And there's actually something equivalent to a glass prism. It's really not a glass prism. I'll talk about what's really used, but it's like a glass prism. I'll deal with that later. And light comes out of the light bulb, and it shines through this test tube. These test tubes that are used in spectrophotometers are very clear glass. They are the same quality glass as a lens. It's known as optical grade test tube or a cuvette. Cuvette is what they're commonly called. So they're just really high quality test tubes with very clear glass. Now, let's imagine we had just water in this test tube. If we have just plain water in the test tube, obviously the light just goes through this clear water, and the light meter is going to indicate 100% transmittance of light. Does that make sense? You're going to get all the light going through. Now, let's imagine that instead of having just water in the test tube, what if we put sugar in the test tube? Now, what do you think is going to happen the more sugar there is in this solution? How is that going to affect the amount of light passing through? Less light. So the more sugar that's in this solution, the less light that gets transmitted through that solution. And that's going to show up on the light meter as less and less light, percent transmittance of light. That's really what it shows here. Here we have a test solution with sugar in it, and obviously less light gets transmitted through it. This is a brilliant idea, because what it's really saying is that the amount of light that goes through a solution is proportional to the concentration of the chemical that's in that solution. So this is the whole theory of how a spectrophotometer can be used to determine the concentration of a chemical in a solution. Now, the guy who first figured this out is actually named after one of my favorite drinks, Dr. Beer. And if you go back to page 1, so Dr. Beer analyzed this relationship between concentration of chemicals in a solution and the amount of light that goes through that solution, and these became known as Beer's law, after Dr. Beer. Now, there are two graphs that are shown here, and I'll walk you through them. We have already told you by the time you're done with this physiology class, you're going to be very good at reading graphs. All right, let's start with this graph. This graph, we always begin first by looking at what's plotted on the x and y axes. So what's plotted on the x-axis is the concentration of the chemical in the solution. Now, I made up numbers 0, 1, 2, 3, 4, 5, 6. That's simply showing increasing concentration of a chemical in a solution. The units are irrelevant. We're simply saying that we're increasing the concentration. It could be in percent concentration, it could be molar concentration, it could be ratio concentration. We're simply indicating increasing concentration of glucose or potassium or cholesterol or whatever the hell it is we're measuring in that solution. What's plotted on the vertical y-axis is the percent transmittance of light. How much light is getting through this solution? Now, notice that here's the graph line, and this graph line shows the relationship. Do you remember how we describe a graph? We always begin as the. If you didn't know that, you do now. We've talked about that before. And you first say as the, and you look at what's on the x-axis, which is called the independent variable. So as the, and what's occurring on the x-axis? Increasing concentration. So as the concentration increases, and then we look on the y-axis. And what is this graph showing as far as what's happening to the percent of light transmitted through the solution? It's decreasing. So the percent transmittance of light decreases. This is an inverse relationship. Inverse means as concentration increases, the percent of light going through the solution decreases. Here's how we would look at this graph. If the concentration was this much, then we get, like almost 100% transmittance of light. As the concentration increases, we get a lower percent transmittance of light. That's exactly what we just said on our, page 2. All right, so there is an inverse relationship between increasing concentration of sugar or cholesterol or potassium and the amount of light that goes through that solution. Only problem here is this is not a straight line. You'd say, okay, so what? This is known in the world of mathematics as an exponential function. That means that if we were using a mathematical description of this graph line, it's going to involve x squared. It's going to be an exponential function. And the problem with exponential functions is that we have to deal with exponents and we have to use logarithms to use this, to convert. We would have to use log functions to convert percent transmittance of light into concentration of a chemical in a solution. Now, we don't want to do any difficult math in this class. We do a number of mathematical things, but all the math is really simple. So when Dr. Beer first saw this, he also didn't want to deal with log functions. So he thought about this, and he thought about it, and he figured out what to do. He said, instead of plotting how the percent transmittance of light changes with increasing concentration, what if we instead consider the inverse of this, not how much light gets through the solution, but how much light is absorbed by the solution. That's called absorbance of light. So you'll notice that on this graph line, again on the x-axis, it's identical. It's showing increasing concentration of the solute in a solution, whether it's sugar or potassium or cholesterol, whatever it is. But what's now plotted on the y-axis is rather than percent transmittance of light, rather than how much light gets through the solution, it's how much light is absorbed by the solution. Now, there are no units for light absorbance, but you'll notice that the graph line that shows the relationship between increasing concentration of chemical in a solution and the amount of light it absorbs is linear. Linear means it's a straight line. And straight lines in mathematics are a beautiful thing. It makes the math really simple. It just becomes arithmetic. No log functions. Let's interpret this graph. How do we always begin when we are interpreting a graph? As the. And then we look at what's on the x-axis. As the concentration increases, right? Then we look at the y-axis, the absorbance of light, and what is the graph line showing? It increases, right? So the more the sugar that's in a solution, the more light it absorbs. And this is, and again, if we have this much sugar in the solution, it absorbs this much light. If we had more sugar in the solution, it absorbs more light. So with a linear or straight line relationship, it becomes very simple math. It's not an exponential function. It does not require the use of logarithms. So what I just described here, in the first case, the concentration is inversely proportional to the logarithm of 1 over the light transmittance transmitted through a solution. We don't like that. We prefer to say that the concentration is directly proportional to light absorbed. All right, so that's the preferred way. Now, there's one caveat. Caveat means condition. What's the condition? Right here. Beer's law only applies if the light going through the solution is monochromatic. What does that mean? It has to be of a single wavelength. Now you might say, well, what do you mean? Well, I want to remind you of something that I think all of you already know. The white light contains all the colors of the rainbow. what looks to us as white light is really a combination of violet and blue and green and yellow and orange and red. And when they're all combined, it looks like white light to us. This relationship between concentration and light absorbance only applies if the light going through the solution is of a single wavelength. Now, why is that? All right, I'm going to mention this. The more chemistry, your knowledge of chemistry, the more you'll appreciate and understand this. All of you have had chemistry. I think all of you have had chemistry. So you learned in your chemistry classes, you have, let's say, an atom. And the atom has the electrons orbiting around in different shells and orbits, right? And you learned that light energy can be absorbed by the electrons, and when light energy of certain wavelengths is absorbed by the electrons in an atom, it raises those electrons to higher energy orbital levels, right? That's called the absorption spectrum of an atom. And you learned about in a chemistry class the light absorption spectrum of hydrogen and maybe sodium. And then, interestingly, when these electrons that have gained energy and are in a different energy orbital level, when they drop back down to their lower original orbits, they release light energy, and that's called an emission spectrum, right? So there's an absorption spectrum of certain wavelengths of light and an emission spectrum. The point is this. Different atoms and different molecules absorb and emit different colors of light. So certain colors of light work better in being absorbed by certain atoms and molecules than other colors of light. So this method only works when you're using the right color of light to cause the electrons to be absorbed, to absorb that energy and move to higher orbital levels. Okay, if you follow any of that, great, and if you didn't, don't worry about it. This is not a course in chemistry. We just use chemistry. Now, how do we ensure that the light going through this solution, which is going to be that chemical in the solution, whether it's glucose or potassium, is going to be absorbing certain colors of light? How do we make sure that the light is only of a single wavelength? All right, so I think you all know that if you had white light and you use a glass prism, if you pass white light through a glass prism, it breaks apart the light into all the colors of the rainbow. In fact, some people know that they're actually, this week we read the story of Noah and the rainbow. But anyhow, that's a whole other thing. But what is a rainbow? Every little droplet of water in the air acts like a little prism. And it breaks apart sunlight into all the colors of the rainbow. That's how a rainbow is created. The little droplets of water that are floating in the air after a rainstorm act like a little prism. And it creates, it breaks apart the white sunlight into the rainbow. That's how it works. So we could basically use a prism to break apart white light and just aim light of a single wavelength through that solution. So, on page 2, the way I represented this right here on page 2 is here's our light bulb. It's giving off white light. We insert a prism, and we can aim just blue light or green light or orange light through this solution. Now, in fact, they really don't use a glass prism. They use a device that you might have learned about in a chemistry or physics course that's known as a diffraction grating. But the way that a diffraction grating works is essentially the same as a prism. So that explains why on this machine there's a wavelength control. When you turn the wavelength control, it's in fact actually aiming light of a single wavelength through that solution. And you can determine which wavelength or color of light it's aiming through that solution. So on page 3, we mentioned that on page 3, a diffraction grating, which basically works the same as a glass prism, is used to aim light of a single wavelength through the solution. All right, now, let's take a look at the bottom here. So, on the bottom, here's how this whole method works. In order to determine the concentration of glucose, or potassium, or cholesterol in blood, or in urine, or in any solution, we first need to know a known solution and what its light absorbance is. So let's imagine that I prepared a sugar solution. Let's imagine I prepared a sugar solution. I took 100 milliliters of water and I put 40 milligrams of glucose in this 100 milliliters of water. That's a 40 milligram % glucose solution. I can take a little bit of this and I can put this in a spectrophotometer and measure its light absorbance. Does everybody follow that? So that would mean I have a known solution and I measure its light absorbance. Here, that would be shown right here. I can have a known solution and I measure its light absorbance. Now let's imagine I have an unknown. I take a sample of blood or some other solution. I don't know what the sugar concentration is in this, and I can put it in the spectrophotometer and measure its light absorbance. So, what I would have then is I would have my known solution and its light absorbance, and I would have the light absorbance of an unknown. Now, if I know this, and I know this, and I know this, can I solve for this? It's that classic kind of formula business that if I've got 4 things here, and I know 3 of the 4, I can solve for X, what I don't know. So rearranging this, so I solve for concentration of the unknown. The concentration of my unknown is simply the concentration of the known solution multiplied times the absorbance of the unknown divided by the absorbance of the known. Does everybody follow that? So it's really simple. There's only one more problem. You'd say, what's the problem? The problem is this. It's a concept you learned about in chemistry also. The problem is accuracy and precision. I'm not going to get into all the details of the problems of accuracy and precision that you deal with in a chemistry class. Anybody remember the difference between those? So the way we commonly describe the difference between accuracy and precision is using a bullseye, like with a dartboard. So if you throw 3 darts, and I throw 3 darts, and the first one's there, the second one's there, and the third one's there, how is my accuracy in getting a bullseye? Not very good. None of the darts ended up in the center. So my accuracy was poor, but how was my precision? Very good, because they're all getting in the same place. So accuracy has to do with whether we actually determine the true value, but precision has to do with the consistency of my results. When you took a chemistry class, did you ever have to weigh a beaker? And you probably noticed that if you weighed it 3 times, you probably got 3 different weights. Why don't we get perfect weights each time? Our scales are not perfectly accurate or perfectly precise, and neither are we in even reading the scale. So the problem is, these problems that you learn about in a chemistry class are equally applicable to determining sugar concentrations in the blood. That when we run these tests, we have the same problems of both accuracy and precision.
What was precision again?
Precision is consistency of result. We could be consistently wrong, but at least we're consistent. So if you're weighing a beaker, or you're even weighing yourself, whatever your true weight is, you may be getting the wrong weight, but if you always get the similar result each time, you're precise but not very accurate. Yep?
How do people come up with accuracy? Is it something like has been proven, or?
Well, we have to assume there is a true weight to a beaker. There is a true concentration of sugar in your blood. But when we start, you've had chemistry classes. Did you ever do experiments? So every time you weigh something, don't you usually get something different?
No, I understand. I'm just saying, like, where the accuracy comes from. Like,
Where do we get it?
yeah.
Well, in other words, there are all kinds of statistical analysis to try to determine this, and we get into things called standard deviations and standard errors, and the average of the mean, and all that kind of stuff. Anybody have courses in statistics? All right, so that's when you deal with all this stuff. Anyhow, these are whole big problems. That this is not a course in chemistry, but these are things that you're introduced to as challenges that are equally applicable to the health sciences. All right, the problem with what we were saying here is we were going to determine the concentration of, say, sugar in the blood using one known point. In other words, I had prepared a known sugar solution, and I measured its light absorbance, and then we took the unknown, let's say it's a sample of blood, and we measure its light absorbance for sugar, and then we're going to solve for what the sugar concentration is in this unknown. But we're putting all of our bets on this one known solution, realizing that we never make these totally accurate. So it would be better, it would be more accurate for me to make many different known solutions rather than one known solution. It's like the more darts you throw, the more likely you're going to get a bullseye. If you're trying to determine let's say, who's most likely to win the next election, the larger your sample size, the more accurate your results. Is that fair to say? If you ask one person, then it's not very accurate. If you ask 1,000 people, it's more accurate. If you ask 10,000 people, it becomes even more accurate because your sample size is bigger. All right, so on page 4, this would be a better approach. A better approach is not to make one known solution, but to make many known solutions. So let's imagine I prepared a 30 milligrams percent glucose solution, and I prepared a 50 milligrams percent glucose solution, and I prepared a 60 milligrams percent glucose solution, and I prepared a 70 milligrams percent glucose solution. I have prepared many solutions. And I measure all of their light absorbances. I now take this information and construct a graph. This graph shows the relationship between concentration of glucose and the amount of light that is absorbed. This graph is not based on one data point, it's based on multiple data points. And it's more likely to give us more accurate results than using just one known solution. So again, just to see how this was done, and you do need to know how it was done because next time you're going to be making graphs like this. So you can see we have 30 milligrams percent was a light absorbance of 0.25. So here's 30. On the graph line, right? 20, 40, 60, 80, 100 milligrams percent. Here's 30, and the light absorbance for 30 milligrams was 0.25. Here's 0.25, and that's the data point. All right, and then we have a 50 milligrams percent glucose solution with a light absorbance of 0.38. So here it is, 50 milligrams percent, 0.38. There's the data point. All right, so here's the data points for these 4 solutions. Yep?
So every chemical has its own light absorbance Meaning
No, this is all glucose. These are just,
I know, because you know how you're mentioning there's
Yes,
no notes, so
that's
how do I know
right.
it's not calcium and it's not like
we would use different wavelengths of light to measure different chemicals. So if we're measuring potassium levels, we're going to use a different color of light or a different wavelength of which potassium absorbs that wavelength, and we'll use a different color or wavelength of light for glucose or cholesterol. And it just has to do with, and you learn some about this in chemistry, and you learn even more in organic chemistry. Right? Who's had orgo? All right, so did you cover all kinds? You learn about UV absorption and infrared absorption, and that's really what you spend a lot of your lab time on is absorption spectra of different organic molecules, right? Yeah. And use those absorption spectra to determine what kind of chemical it is. Anybody ever do gas chromatography? All right, so gas chromatographs use another method of absorption spectrums to identify what the molecule is. So, but again, this is not a course in chemistry, so I don't want to go too far on this.
so as long as it's a different wavelength, then you know you're measuring the
Exactly.
concentration.
You're able to use different wavelengths to measure the concentration of different chemicals. All right, so we have now constructed a graph, and then we draw a line that best fits these data points. I want to emphasize that when we do this, not only did we use these known data points, there's one more data point that's known, and that's called the blank. The blank is when we usually just use plain water. And when we have plain water, there is zero amount of light that's absorbed. We actually zero the machine out to ensure that when we're just using the so-called blank, which is usually just water, the main point of what a blank is a solution with zero amount of the chemical we're trying to determine. Has everybody got that? You should know what a blank is. A blank is a solution with zero amount of whatever chemical we're trying to determine. So you can use, a blank could be any solution with, if we're trying to measure glucose levels, there's zero glucose. If we're trying to measure potassium levels, there's zero potassium. That's the definition of a blank. It is blank or zero for whatever we're trying to determine.
Is still water we use or just regular water?
Well, again, as long as it doesn't have to be water, it could be even blood plasma, it could be anything. The definition of a blank is, make sure you know this, because I'm going to ask it, zero amount of whatever we're trying to determine. So it's irrelevant whether it's deionized water or regular tap water. The point is it's got zero amount of whatever we're trying to determine in it. So since it's got zero concentration, it will have zero absorbance of light, of whatever we're trying to determine. Now, that when you construct these graph lines, it's got to go through the 0, 0 point. That's called your blank. Now, let's make sure we understand what's going on here. We look at these data points. Why didn't all these points line up perfectly in a straight line? Problems of accuracy and precision. All right? So all we do, and all that we're going to do in this class, is we draw the best fit. The best fit does not mean that we ignore any data point. We cannot ignore a data point. What we do is we try to make our line go as the closest we can to all the data points. We do not ignore a point. So in other words, this point was not ignored. That line still has to be as close as possible to that point while still being close to this point. In other words, you might have said, let's draw this line so it goes through at 2 of these points perfectly. That's not how we draw. Now, you might also say, this doesn't seem very accurate. If all I'm doing is eyeballing it and trying to draw the best fit, that doesn't seem highly accurate, and you're right. The way these lines are truly drawn is using what's known as a linear regression analysis, where you take into account the average of the means and the standard deviations around that mean. But I'm not going to get into the statistics. Okay? If you had a statistics class, you dealt with the means and the standard deviations around those means. Okay, so most of your fancy calculators do carry out linear regression analysis. That's how it's actually done. All right, now that we've constructed this linear relationship, this straight line relationship between increasing concentration of, let's say, sugar and the amount of light that is absorbed by the sugar, now we can take our unknown. Let's imagine, and this is what it shows on the next page, let's say we have an unknown, and we take that unknown and we measure its light absorbance. And it has a light absorbance of 0.35, and there are no units with light absorbance. So we go back to our graph. This is the same graph that was drawn on the previous page. We find 0.35 on the y-axis, that's light absorbance. We draw an arrow to where it hits the line, the linear line, drop a perpendicular down, and we read off the graph what is the concentration of this unknown. And in this particular case, it's about 44 milligrams percent. So does everybody follow how, if you had to prepare a number of known solutions, how you would construct a graph showing the relationship between known solutions and their light absorbance, and then how you could take an unknown solution and derive from the graph you had constructed what its what its concentration was. All right? Because next time we're going to be expecting you to do that. Okay, so this is how it's done. This is, again, most of you had to do this in a chemistry course.
And the linear line that you draw is based on the glucose and all this data.
This graph right here is the same as what was drawn on this page here.
So we just put our
You just took, basically right here, you took this unknown, you had a light absorbance of 0.35, and you dropped it here and got 44 milligrams percent. Now, this, using many known data points, is actually considered more accurate than using one data point. All right, because when we look at this graph line, they don't all line up in a straight line because of problems with both accuracy and precision, but we kind of hope that when we draw that straight line, it cancels out our errors. But we can't just ignore any single data point because we don't know. This data point could be the most accurate of all these, so we can't ignore it.